Hello, everyone. Welcome to my talk on Maven dependency management. Today, we're going to talk about taming Java dependencies in 70 plus GCP client libraries. A little bit about myself before I jump into the talk. My name is Stephanie Wang. I am a developer programs engineer at Google Cloud Platform. My main responsibilities is to manage the Java BigQuery client libraries. I normally write new features and fix bugs in our client libraries. And here is my Twitter handle, Steph Wang Builds. And I also have a website hosted on GitHub, and this is the web link. Before we talk about the Java dependency management in our GCP client libraries, you may wonder, what are these client libraries? So Google Cloud Client Libraries are our latest and recommended client libraries for calling Google Cloud APIs. They provide an optimized developer experience by using the supported language natural conventions and styles. For instance, in Java BigQuery, we offer the BigQuery client libraries that facilitate developers to call the BigQuery APIs more easily. And we provide the idiomatic, generated, or handwritten code in every single server language. And that includes Java, Python, C#, C++, etc. And it usually makes the Cloud API more easy and intuitive to use. We also handle any low-level details of communication with the server. So for instance, we wrap the HTTP transport in the BigQuery client to make it easier for the developers to call the BigQuery client APIs. And if you're interested in learning more about client libraries, please feel free to check out the link that I'm attaching right here, which explains more about what client libraries do and how they can help developers. So now we know a little bit more about what client libraries are. I would like to first share a little bit about the real Java maintainers of 70 plus GCP client libraries, how the experience was maintaining all these client libraries from a dependency management perspective. When you have 70 plus Java client libraries, which is, by the way, I think quite a few of them, dependency conflicts were very hard to reconcile and happened often. So here is a snippet of an upper bound dependency error that I encountered when I was trying to update the Google Cloud Storage client library in the Google Cloud BigQuery client library. So Google Cloud Storage is also one of the Google APIs client library. So as you can see, we're trying to upgrade a Google client library within another Google client library, yet we encounter upper bound dependency errors like this. So essentially, the Google Cloud BigQuery client depended on the Google Cloud Core artifact, which pulls in protobuf Java util artifact, and that had an earlier version of protobuf Java util. However, the Google Cloud Storage already upgraded the protobuf Java util dependency, and now that's a later version. So because of that, that introduced an upper bound dependency error when we're trying to upgrade GCS in BigQuery. Right. And very similarly, Google Cloud BigQuery also depended on the Google Cloud Core HTTP artifact, which depended on the Open Census API dependency. And that was an earlier version, 0.24.0, right? And the Google Cloud BigQuery also depended on Google Cloud Storage, which is the dependency that we're trying to upgrade. And that pulled in a later version of Open Census, which is 0.25.0. Now, because of that, we had another upper bound dependency error. So these were just some examples of the common errors that we observed while trying to manage our client library dependencies. There were 104 dependency update PRs in the BigQuery client libraries alone from January to March 2020. That roughly is about one per day. And that was a lot for us. And this is pretty much how I felt each day when I had to deal with all these dependency update PRs and oftentimes upper bound dependency errors when we're trying to update. So to understand our problems better, we were trying to, first of all, reduce the number of dependency update PRs across our client libraries. And number two, reduce the number of upper bound dependency errors during dependency updates. And that translates into, number one, stop managing common dependencies individually in each client library, right? So if two of our client libraries, for example, Google Cloud Storage and Google Cloud BigQuery, both dependent on one of the common dependencies. So perhaps we could simply manage that one particular dependency in one place. So it would be easily aligned underneath our client libraries, right? And number two, more importantly, we wanted to use consistent versions of the same dependency to ensure dependency convergence across our client libraries. That means ideally, we should be able to bundle up all the common dependencies to manage their versions at one place, and also pull the commonly managed dependency version easily into each client library. So how do we achieve that? That's when we introduce the Google Cloud Shared Dependencies BOM to our client libraries. So before I go more into details of what our Google Cloud Shared Dependencies BOM is composed of, maybe we can first talk about what is a BOM. So if you're not familiar, a BOM is a special kind of POM file that Maven allows us to define the versions of our dependencies or transitive dependencies. So in this particular POM file, we declare the versions and scopes of these dependencies that we want to manage. Essentially, it is a centralized place for us to mention all the dependency details. It is one of the best practices in our JLBP, which is the Java Library Best Practices, number 15, to publish a BOM for multi-module projects for better management. Importing this BOM basically means that dependency versions from this BOM will be used in your project. So it really is a very convenient and a great way for us to manage our dependencies across the board. So what we did was we bundled up all the common dependencies used across all our client libraries. And these dependencies included things like gRPC, GAX gRPC, Guava, protobuf, API common, etc., etc. So we did the research to figure out what are these common dependencies used across all our client libraries. And then we put all these dependencies into the Google Cloud Shared Dependencies BOM. And then each API-specific client libraries, such as a BigQuery client library, is now importing this particular BOM. And this means that every single library is now using the same version of dependencies, meaning these shared dependencies. So we no longer faced any upper bound dependency update errors when we're trying to update two client libraries that share the same dependency. And on top of that, the number of dependency update PRs reduced dramatically from 104 in Q1 2020 to only 31 in Q3 2020. That was great. However, BOM is only part of the solution. It also introduced new problems. It didn't just work perfectly. So let's imagine a scenario. Suppose we are talking about the PubSub client library, which has two direct dependencies on GAX gRPC and Open Census. And both of them depend on gRPC artifacts. And on the left-hand side, you can see GAX gRPC is pulling in an older version of gRPC. And on the right-hand side, you can see that Open Census is pulling in a later version of gRPC artifact. Now, basically, this means that we have a dependency misalignment issue, which could potentially introduce dependency conflicts to our customer. Now, a very good way to manage the gRPC artifact is to import the gRPC BOM, right? So if we want the later version of gRPC to be used, then we can simply import the gRPC BOM. Now, remember what a BOM does is for us to simply manage dependency versions and scopes in our project. So yes, if the PubSub client library imported the gRPC BOM 1.10.1, the later version, That would help us manage the transitive dependency versions over here from 1.0.1 on the left-hand side to 1.10.1. And voila, we have dependency alignment. That is great. However, things get more complicated when the user's app come into the picture. So if suppose we have a library consumer, here we call it the user's app, that depends on the PubSub library. Now, what version of gRPC is the user's app using? And now I would like to pause for a second just for you to think about it. What version of these gRPC artifacts do you think that the user app is actually using? Think about it. So a lot of people probably think that the gRPC artifact version would be 1.10.1 because look, we're trying to manage the version of gRPC artifacts over here by pulling in the gRPC BOM into the PubSub library, right? We're importing this BOM in order to manage the versions of gRPC artifacts in the PubSub client library. And that is what a BOM does. So yes, it should be 1.10.1. However, that is actually not the case. Now, if we inspect the dependency tree, the actual version of gRPC that the user's app is actually using is going to be 1.0.1 on the left-hand side still. And this is an observation that we discovered while we're trying to resolve some of the dependency issues in our client libraries. And we coined the term loss of transitive dependency version, where when you're trying to manage the versions of your transitive dependencies using the BOM strategy, the user's app actually can get the managed transitive dependency versions successfully. So one way to address this issue is for the user's app to directly import the gRPC BOM, right? So if they did that, then the gRPC BOM can successfully manage the transitive dependency versions and make sure that the gRPC versions are now, again, the higher version, 1.10.1. But the challenge over here is the user would have to go and figure out what the client libraries is actually using for the gRPC version. They have to first go and find the gRPC version, and then they will have to declare this BOM version in their POM file. And that is a lot of work. So this is not a preferred way, and it's the kind of burden that we would rather not have to exert onto our users. Now, alternatively, and this is a strategy that we went with, was to lock in the versions. Now, what do I mean by that? So there is an existing open source plugin that is developed by Mojo House called the Maven Flatten plugin. And what it does is it encodes the version specified by the BOM into the POM file, and then it gets it published to Maven Central. Essentially, in each client library, we have an original POM.xml file, and then we use the Maven Flatten plugin to flatten the original POM.xml file, and then that becomes a flattened POM.xml file, and then we publish this flattened POM file to Maven Central. So here is an example of the Google Cloud BigQuery POM.xml published in Maven Central. Now you can see that we have a lot of exclusions here, and this POM file is definitely longer than a typical POM file because it's flattened. Now, what are the benefits of doing that, right? So the benefit of doing this is it allows us to lock in the actual versions of every single dependency, direct or transitive, that are used by our client library. So instead of having the kind of tree structure that we saw over here that gave us the loss of transitive dependency version issue, now if we think about the PubSub library, we are directly specifying every single gRPC artifacts version, and that's going to be the higher version. This is good for us because we can ensure and guarantee that our users are going to be getting access to this specific version of gRPC, which is the version that we build and test against in our client library. But obviously, transformation of POM files can be risky. ultimately, we are converting the original POM file to the flattened POM file. So to ensure that we're not introducing new dependencies or altering our POM files in any way that's unnecessary and incorrect, we developed a script to constantly check for the correctness of the transformed flattened POM.xml. The first thing we check for is the resolution order. We want to make sure that we are still sticking to the original resolution order when we're transforming the POM file. And secondly, we're checking for the POM file completeness, meaning all our runtime dependencies are the same. So here is a section of our script where we're comparing the dependency list of our POM files, ensuring that everything is correct in terms of the order and in terms of comprehensiveness. So what's happening now is if a user is pulling in the PubSub client library and also the BigQuery client library, these two libraries are directly importing the Google Cloud Shared Dependency spawn to manage the common dependencies version. And because they're flattened, we know that the user's app are going to be getting the exact versions that we build and test against from the shared dependency spawn. And also they can be pulling in some other bombs like gRPC core. And again, because our client libraries on this level are flattened, we again ensure that our user apps is getting the version that we think they are getting. What does this mean for our users, right? One of the reasons why we adopted the Maven Flatten plugin is for us to better manage our dependency versions. But I really want to just share a use case with you to kind of show you how this way of managing dependency also helped us directly address a customer issue. So just a couple weeks ago, I had a customer issue where one of our client libraries, the Java BigQuery client library, had a security vulnerability introduced because of an older version of Commons codec that is transitively pulled into our client library. So here's some more descriptions of this particular CVE. And here is the snippet of our dependency tree. As you can see, the Google Cloud BigQuery artifact depends directly on the Google HTTP client dependency, which depends on the Apache HTTP client, which then depends on Commons codec. So from the Google Cloud BigQuery's perspective, this Commons codec 1.11 is an older transitive dependency. Now, how do we then make sure that we successfully manage this Commons codec dependency in order for us to address this CVE? So what we have to do is to upgrade the Commons codec dependency from 1.11 to 1.15, where a fix was put in, a security fix was put in, right? So one way that people thought was, okay, why don't we just use the dependency management section of the Google HTTP client artifact, which we have control over and we can modify and release easily, and specify directly the Commons codec version and make sure it's 1.15, right? Actually, a pull request was made exactly for that, right? If you can see over here, so a software engineer made a pull request to specify the Commons codec dependency version 1.15 in the Google HTTP Java client artifact. Now, this is not going to work because, as we can see, that this Google HTTP Java client is not actually flattened. So if we went to the POM file of this repo, right, nowhere in here can we find the flatten plugin being implemented. So this way of solving the issue is exactly how the loss of transitive dependency version comes into play, right? So it wasn't going to work for us. What did work for us was to use our Google Cloud Shared Dependencies to manage this version. So instead, we're declaring the higher version of Commons codec in the dependency management section of our Google Cloud Shared Dependencies artifact. And why does it work? And the reason is because we are flattening the Google Cloud BigQuery artifact, right? So the Google Cloud BigQuery artifact, again, like we said earlier, is directly importing the shared dependency spawn, right? And now the commons codec is going into the shared dependencies BOM. And because we're flattening this artifact, that means our users are going to be getting the correct version of commons codec, which is a transitive dependency for them, and which is going to be 1.15. So I know I probably went over this case pretty quickly, but I really encourage you to think about it and really truly understand the significance and really the subtlety of this loss of transitive dependency issue and how we were able to address it successfully by using the flatten plugin, right? So to summarize, a combination of the Google Cloud Shared Dependencies BOM and the flattened client library resulted in our resolution and solving of this customer issue. Now, what does this all mean for our end users, library consumers? So obviously, this is one of the examples of how the application of the flatten plugin helped our library consumer directly. But even on a broader scale, consider if a customer, or say a library consumer, wants to use the BigQuery data transfer and PubSub Java client libraries to schedule data transfer jobs with real-time PubSub notifications. How do we then make sure that these two client libraries are going to work compatibly? So ultimately, we want to achieve client library compatibility in order to avoid any potential dependency conflicts for our end users, right? One way is to directly use the Google Cloud BOM. So again, like we mentioned earlier, the BOM strategy allows us to successfully manage the dependency versions in every in your actual project, right? So all these common dependencies go into the Google Cloud Shared Dependencies BOM, which go into our API-specific client libraries like the PubSub client or data transfer client or BigQuery clients. And then all these API-specific client libraries go into the Google Cloud BOM. So the user can simply import the Google Cloud BOM, which then will automatically manage the versions of the BigQuery data transfer client and the PubSub client. And that's great. However, this is not a 100% foolproof solution for every single one of our customers. A lot of our customers are not able to use the BOM strategy because they're using SBT, for example, or they prefer managing their dependencies independently. So what we did was to develop a dashboard to help our customers find out compatible versions of client library, right? So here is an example of our dashboard, right? And I'm going to jump into a bit more details of how we are able to make use of this dashboard. So here is an actual customer issue that I helped resolve, again, earlier this year. So one of the customers, Data Fusion, wanted to upgrade to at minimum version 1.124.5 of the BigQuery client library in order to get access to a number of new features that we released. Now, this is a very common use case. A lot of our GCP customers would only consider upgrading their dependencies when they see that, you have a new feature that I want to get my hands on. So in this particular case, I believe they want to get access to the time partitioning feature that was more granular. And that's when they decided to upgrade the dependency version of our Java BigQuery client. However, it was not going to work for them if they only updated the BigQuery client version because this particular customer also had other GCP dependencies like Bigtable, PubSub, Spanner, Speech, Storage, and Data Store. By upgrading only the BigQuery client version, they introduced dependency conflicts because these clients all shared a number of common dependencies under the hood. And dependency misalignment was becoming an issue for this particular customer. Now, going back, our solution one, I immediately recommended them to use the BOM strategy, right? Remember, you can use the BOM. You don't even have to specify your dependency versions. The BOM does it for you. So just directly import the BOM and it just solves all the problems for you. However, this particular customer did not want to go for the BOM strategy. They were not ready to migrate to using the BOM. And also, this is a very common scenario. Not everyone is open to convert from managing their dependencies to just relying on BOMs completely. So they particularly prefer managing their own dependencies and remain flexible in their version management. So now the question is, how do we help them find compatible client libraries that will 100% not introduce any dependency conflicts, meaning guaranteeing that all these client libraries are going to work compatibly with each other. And these client libraries included everything in this list, right? So this is exactly when the Google Cloud dashboard, Google Cloud BOM dashboard came into use. So all I had to do to solve this problem was to first identify the version of the Google Cloud Shared Dependencies BOM that is being used in the Google Cloud BigQuery client. So they wanted version 1.124.5 for Google Cloud BigQuery. So I came here and I just put in 1.124.5. And in this case, Google Cloud BigQuery is the only artifact that had that version, so they pulled up for me. But this dashboard, as you can see over here, also accepts column names and then version. Right, so from here, I know that this version of Google Cloud BigQuery is using 0.15.0 version of Google Cloud Shared Dependencies BOM. Now, what we have to do next is to locate the versions of the other client libraries that use the same version of the Google Cloud Shared Dependencies BOM. Why? Because these other client libraries are going to be sharing the exact same underlying versions that are included, bundled up into the Google Cloud Shared Dependencies BOM, making sure that there's not going to be any dependency conflicts, right? So now we just type in 0.15.0 over here, which is going to pull up all the artifacts in all different versions of the Google Cloud BOM that have this Google Cloud Shared Dependencies BOM version 0.15.0. And now I can simply go and check out, what version of Spanner, for example, I can use compatibly. And I have the option of using Spanner 3.0.3 or 3.0.4. And also, if I look down here, I also have the option of using the Google Cloud Bigtable 1.18.0. So now using this way, we're able to quickly identify the versions of the client libraries that we're going to work compatibly with each other. These are the versions, and we're able to help our customers directly solve their dependency issue. So I guess what we're trying to say here is, the combination of using this dashboard and also using the Google Cloud Shared Dependencies BOM and the Flatten plugin ensures that we're able to help our customers find out the compatible versions of client libraries very easily. And we're also confident that we are giving them the dependency versions that we build and test and know that we're using in our client libraries because we're flattening our client libraries. So the combination of these strategies is very, very powerful. So I have a Medium article on debugging the Maven Flatten plugin that's published, and I welcome you to give it a read if you're interested in checking out the Maven Flatten plugin, how to use it, and some of the work that we did to make sure that it works for our use case, to make sure that we're able to flatten our client libraries and give our customers the correct version of transitive dependencies. Thank you very much for attending the talk today. And I really hope that I was able to give you a quick overview of how we managed to tame dependencies across our 70 plus GCP client libraries by using the combination of strategies of using the BOM, the Google Cloud Shared Dependencies BOM, and also the Maven Flatten plugin. And I really hope you get to try this out in your project as well, if the use case is applicable. Please feel free to follow me on Twitter or ask me any questions after this. Thank you so much for your time.